Hi, these are the notes on section 4-1 antiderivatives and indefinite integration. And I'm going to start at the top. It says suppose f of x equals 3x squared. Find a function capital F who has as its derivative f of x. And by that I mean if f of x is the derivative, what type of function did it come from? Well, if you kind of reverse the power rule, you know that you're going to have x here, and since I have an exponent of 2, I must have started out with an exponent of 3. And it's looking to me like it's x cubed. And so if I take the derivative of x cubed, I would have, to take the derivative, I would take 3 times the coefficient 1 that's in the front here, and subtract 1 from the exponent, and I would get 2. And sure enough, 3x squared is the derivative of x cubed. So that works. And then I give you this example right here that says, alright, let's say we had a function f of x, and it's equal to x to the fourth, and you took its derivative, or f prime, and you get 4x cubed. Well, that means that if I start with 4x cubed, f prime of x equals 4x cubed, and I worked my way backwards with this double arrow type of thing, I would get that f of x is equal to x to the fourth, which is what I have here, x to the fourth. Alright? So a couple of things is that when you have a capital F, that's what we're going to call the antiderivative of a lowercase f. So lowercase f we're going to use in this particular text to represent derivative, and capital F as its reversal. The function it was before the derivative happened, or what we call the antiderivative. Now, technically speaking, it doesn't have to be x cubed. It could be x cubed plus 4, it could be x cubed plus 5, it could be x cubed plus pi, because when you take the derivative of those constants, you get 0. In other words, we can say it's x cubed plus c, and c is we're going to call the constant of integration. I'll talk about that in a bit. So anything that's in this form is called a family of antiderivatives, or it's called the general antiderivative of f. It's also sometimes called the general solution of f. Okay, and we'll get to that down the road a little bit more. Alright? So I want to go and graph, first of all, this general solution and talk about what it looks like. And I'm going to pull up a calculator here. And I'm going to graph. And my guess is I got a function here that I got to delete. And so I'm going to have x cubed, and then I'm going to have x cubed plus 1, x cubed minus 1, and I'm going to do a couple more here, x cubed plus 2, oops, and x cubed minus 2. Okay, and I'm going to graph these. And I got to make sure I want my window the way I want it to be. I don't. Standard. Okay, and so you can see these graphs, and really one is right up above the other, and they're just sliding up here. And so as I move up the y-axis, or as I move down the x-axis, I would have a bunch of graphs that look like this. They're all exactly the same, except one is slid up or down compared to the other one, and this is what we're calling our family of graphs. I just want to give you a picture of what that looked like. So that's our family of antiderivatives. Alright, the operation, let me just back up a little bit. The notation for antiderivatives is this: is if you see this symbol, this means you find the antiderivative of 3x squared dx, and that antiderivative is x cubed plus c. This is read: the antiderivative of 3x squared is x cubed plus a constant. In general, dy dx equals f of x. Okay, so the derivative equals f of x. Well, if I multiply both sides by d of x, I get dy equals f of x times dx. We're going to use this form, and the reason we're going to use this form is in a couple of sections we're going to redefine what this means, and this dx is going to be the width of a rectangle. And you'll forget that in a little bit that I even said that, but don't feel strange that this dx is tied to this f of x. It's going to make sense down the road, and simply it comes from this equation right here, multiplying both sides by d of x. Next, the operation of finding all solutions to this equation is called antidifferentiation or indefinite integration, and I use the terms indefinite integration a lot. So again, this means you're going to take find the antiderivative of f of x dx, and that's going to give you capital F of x plus c. This symbol right here is called the integral symbol. F of x is called the integrand. D of x is called the variable of integration. F of x is the antiderivative of f of x, and c is your constant of integration. Alright, some rules to finding antiderivatives. First thing to remember that the derivative process and the antiderivative or integration process are inverses of each other. One undoes the other. That's a big idea. If you think of addition, when I take 5 plus 2 and get 7, there's a related subtraction problem. Actually, there's two of them. 7 minus 2 is equal to 5, and 7 minus 5 is equal to 2. So for this addition problem, there is two subtraction problems. The same thing happens in multiplication. If I have 3 times 4 is equal to 12, I come up with two division problems. 12 divided by 3 is 4, and 12 divided by 4 is 3. Likewise, if I take the derivative of x cubed plus 4, I only get one answer. That's 3x squared. However, if I find the antiderivative to 3x squared, I have an infinite number of antiderivatives because the constant can change. The constant can vary, and it allows me to have a whole family or a whole infinite number of antiderivatives for that one derivative. Alright, couple of things here. Here's some integration. On number 2, the biggest thing, just like when we took derivatives, like if we had f of x is equal to the square root of x, when I taught you how to take the derivative of that, one of the first things I had you do is write that in exponential form, x to the 1/2. Likewise, we're going to do the same thing. When we're figuring out antiderivatives, what we're going to do is write them in exponential form and reverse that process. More about that in a bit. Alright, let's take a look at our integration formulas. If I finding the antiderivative of 0 dx, that's going to be c. And if you should take the derivative of c, you should end up getting 0. Likewise, if I'm integrating some constant dx, such as even 3, I'm going to get kx plus c. Take the derivative and go backwards. The derivative of c is 0. The derivative of kx is k. You should get this integrand in here when you reverse the process. When I take the integration of k times some function, that is equal to k times the integration of f of x dx. When I'm integrating the sum or difference between two functions, that's like integrating them separately. This is the one I want to talk about the most. Right here is e. And it's this idea of if I have something to a power. So let's take a look. And we kind of did that a little bit. If I'm taking the antiderivative of x squared. Remember, when I take the derivative of my result, I should get, excuse me, sorry about that. When I take the antiderivative, when I take the derivative of my answer, I should get x squared. So let's see what we're going to get here. First thing I write down is my plus c, so I don't forget that. And then, since I have a squared term here, I know I'm going to have a cubed term. Now, if I take the derivative of this, I get 3x squared. But I don't have 3x squared. I have just x squared. So what do I need out front here that when I multiply it by 3, I get a 1? Well, that number is going to be 1/3 x cubed. So likewise, let's take a look at another one. Let's say I have x to the 6th dx. What is that antiderivative? Well, it's going to be plus c. I'm going to have x to the 7th. And again, I'm going to need something out front here, so I get this 1. Well, that's going to be 1/7. Well, look at the relationship of this denominator and this exponent. Look at this denominator and this exponent. And if you take a look at they're exactly the same. So if I have something like, let's change it up a bit, 5 x to the 11th dx, I'm going to have 5 x to the 12th, but, don't forget your plus c, but if I take 12 times 5, I get 60, and I need 5. I'm going to have this denominator be 12. And if you notice, I'll take 12 times this 12 that's in the denominator, and then I'm left with this 5. So what I can say here, if you notice this, I added 1 to the exponent, and then I'm dividing or multiplying by the reciprocal, but in that same exponent, n plus 1 is in the denominator. We're going to look at some problems in a bit. Alright, if we go backwards here, the antiderivative of cosine dx is sine x plus c. Again, if I take the derivative of sine is cosine. The antiderivative of sine of x dx is a negative cosine dx, because when you take the derivative of cosine, you get a negative sign, so I need to multiply it by a -1 to make it a positive sign. The antiderivative of secant squared x dx is tangent x plus c, because the derivative of tangent x is secant squared. The antiderivative of secant x tangent x is secant x plus c, because the derivative of secant x is secant x tangent x. The derivative of cosecant squared x dx is equal to negative cotangent squared x plus c, because the derivative of cotangent is negative cosecant squared x, and I need to multiply that by a negative to make this a positive, my integrand positive in the inside. The derivative of the antiderivative of cosecant x cotangent x dx is a negative cosecant x plus c, because the derivative of cosecant x is a negative cosecant x cotangent x, and I need to make it negative to make this particular thing inside positive. Alright? These, by the way, are all in the front of your book in that blue section.